So we got our clock circuit working here, but as we go through our project, we're going to want to test and debug our circuit. And in those situations, it's going to be very useful to have a manual control over the clock instead of it just automatically blinking on. And the circuit on the right performs that function. So anytime we need a clock pulse, we just push this button and one is generated. And all this circuitry here on the left of our push button, that performs two functions. The first and main one is that it debounces our push button, and it also sets the length of our pulse. And to do so, we've used the 555 timer, but this time hooked up in its monostable mode. And it's similar to the A-stable one, but with a few differences. And one of those differences is that pins 7 and 6 are tied together, whereas pin 2 is on its own. And the components we add are this 100 kilo ohm resistor and a 1 microfarad capacitor right down here. Now, normally we're going to want to have like a flat line at 0 on the output. And to have that, we have to keep pin 2 here high at 5 volts. And this is accomplished with a 10 kilo ohm pull-up resistor. And you can see our push button is right here. So once we push down our push button, pin 2 is obviously going to be connected to ground, and this is going to cause our output to go high. And once our output is high, the discharge pin here is suddenly going to become an open circuit. And once it's an open circuit, well, current's going to flow down through this resistor and start charging our capacitor here. And as our capacitor charges up, the voltage across it is going to, of course, rise too. And once it reaches the threshold voltage, well, the output is suddenly going to snap back down to ground and then continue on. And at the same time it snaps to ground, the discharge pin is going to snap to ground as well, and our cap is going to like quickly discharge just immediately because there's no resistor in its path. And so that's kind of how we produce our pulse over here. And the length of this pulse is given by this equation. So it's just the RA times the capacitor. And for the components here, that comes out to about 0.1 seconds. Now, if you look here, it seems to work. However, if I pushed it and hold down, you can see the pulse stays on. And so it's going to stay on for as long as I hold down. And that might not seem so bad, but it actually poses a problem with our debouncing mechanism. And to see that, we gotta go check it out on the oscilloscope. Okay, so we have our monostable operation on the 555 timer hooked up to the scope, and it shows just what we expect. The blue trace is our trigger pulse that jumps from 5 volts to low for a brief moment and gets back up to 5 volts. And the yellow trace is our output pulse. And right here it shows the width of that pulse, and it's about 127 milliseconds. So it's kind of close to the 110 predicted by the equation. And of course that's the voltage of the capacitor charging, and you see it suddenly drops at the end. Now this circuit works fine so long as the width of the trigger pulse is within that 127 milliseconds. As long as it's not longer than our output pulse, then all the debouncing is taken care of. However, if it is longer, then all bets are off. And maybe we could see that. So let's see if we could catch some debouncing in the circuit, in our circuit here. If my push button will cooperate and start giving us a messy signal. There we go. So now if we zoom up, we see that our trigger has gone up and down a few times, but more importantly, the yellow pulse, you can see clearly goes down and then comes back up. And so with one push of the button, we get 2 output pulses. Oops, wrong one. And that's not quite what we want. And so, let me turn off the power. And so we could deal with this situation with the use of a high-pass filter. Here. And by putting in a series capacitor, should do the trick, but we'll need, of course, another pull-up resistor to keep it high. And this could just be another 10K resistor and 0.01 microfarads. And so the way this is going to work, when we push down on a push button and we get that kind of a long pulse like this on this node, over here on this node, it's going to be much shorter. Essentially, before we push down on the button, there's no current flowing, and so there's going to be 5 volts here and 5 volts here at our trigger, which is what we want. But the moment, and since the voltage is the same, there's no charge on this capacitor. And so the moment we push this to ground, this is going to be suddenly forced to ground. But since there's no charge on the capacitor, there can't be a voltage across it. And so this node here is going to it's going to suddenly drop right back to ground too. And once this is at ground, well, it's going to start, the capacitor is going to start charging up through current coming through this 10K, and it'll charge up the capacitor like so. And then once it reaches its 5 volts, it's going to continue on. And now we could control the width of this pulse basically through the time constant of these 2 components. So it's going to be something like 100 microseconds will be the time constant. And so it's going to be in that range, and basically much smaller than our output pulse. And so let's add this this high pass filter to our circuit here. And we'll put a 10 kilo ohm resistor up there, like so. Okay, so we just added our small little cap from the output of our push button to another 10 kilo ohm pull-up, and that goes to our input. And so let's see how this one works. Let me trigger this on the falling. I should probably put the power on. Okay, so we get our output pulse, and there's a capacitor charging, and if we look at our trigger, we see it's tiny. And if we zoom in here, we can see it's a tiny little pulse on the order of hundreds of microseconds. We've got about 200 microseconds per division. And so now, even if we hold on, it's never going to be longer than that. Let's demonstrate again. That's a quick one, and that's a long one. So no matter how long we pull off, it's always stuck at 127 microseconds. And so this is good. Now we've debounced our circuit, and we get the output pulse that we want. But there's one slight problem, and it's this guy right over here. It's this nasty fellow. And if you look right there, it says the max of our blue trace is 7.44 volts. So he's going way past 5 volts, and he's jumping up to 7.5 volts. And this is not good news. This is not good, and we can see why. If we come to, if we look at our data sheet right here, under the absolute maximum ratings, let me turn the power off, it gives as the input voltage for these inputs, and right here on the trigger, max VCC, and in our case 5 volts. So if our voltage is jumping up to 7.5 volts, well that's 50% times more than 5 volts, and that just simply will not do. Oops, wrong one. And so there are a few ways we could deal with this. One way is to sorry, let me just zoom in here. One way is to add a clamping diode. So it's going to look something like that. That goes up to our 5 volts. And essentially is once once it starts to spike up like this, as this voltage rises beyond the forward voltage of this diode, so generally 0.7 volts. So once this becomes, say, 5.7 volts, it's going to start to conduct a bunch of current and clamp our voltage down to 5.7. So 5.7 is a whole lot better than 7.5 volts, but it's still 0.7 volts over the maximum rating. And even if we use a Schottky diode where the forward voltage is 5.3, it's still 0.3 volts over the maximum allowable. And you know, it's just, it says absolute maximum for a reason. You just shouldn't be putting those voltages on those pins. But there's actually a simpler way to deal with this nasty spike here, and we don't need any extra components. So, and that could be accomplished just by increasing the size of this resistor here. So long as we make this resistor much more bigger than this second one here, this will kill off our nasty spike. So we could change this from a 10K to, say, a 1 mega ohm, and this should do the trick. So I got a mega ohm resistor here, and I'll just pull out our 10K and add him to our circuit. Energize the circuit. And now let's see what happens. Okay, so there you go. So we still have it looks a little odd. Let me push it again. That looks better. So we still have our short quick pulse that goes down to ground, and our trigger pulse, and that creates our normal, 127 millisecond output. But here you can see the that positive spike is all but killed. There's just a little bump right there, and the maximum has dropped to 5.04. So we're in the tens of millivolts. So we went from like 2.5 volts to the tens of millivolts. And in fact, we could pretty much go even less if we change this 10 kilo ohm to 1 kilo ohm, and basically there'll be like 1,000-fold difference, and there won't be any hint of a spike. And so now we have our one shot, and it delivers a nice crisp pulse. No matter how long we push down on the button, you can just hold it down, and it just stays the same. So, thanks for watching, everyone. Okay, so for those of you who might be a little interested more in the details of why simply changing resistor values can get rid of a spike, I've drawn out a little explanation right here. And so I've taken away the numbers just to keep it more straightforward. But basically, we have our 5 volts here, which I've called a VCC, and our first resistor with our push button that goes to our cap, and the second resistor up to our VCC, and it's this node that triggers the 555. Now the 555 has a very high input impedance, and so for our analysis we could ignore it, and it's totally fine. It doesn't have much effect on the circuit. So before we push down on the push button, basically no current's flowing, and V1 and V2 equal VCC, in our case 5 volts, and there's no charge on the capacitor. Then, once we push down on this, we force this node to ground. And here we get the our little trigger pulse that we want. And of course, this is this little capacitor charging up here. So the capacitor is going to charge up to 5 volts or to VCC. And so over here, at the moment we release that push button, right at the moment, we're still going to have our 5 volts across the capacitor, or the VCC here. But the question is, what is V1 and V2 going to be? What are those voltages going to be? Because when we're pushing down on the capacitor, you know, that's what forced it to charge. But its normal state is to be, over here, is to be uncharged. And so the moment we release it, this capacitor is going to want to discharge itself, right? And what's going to happen is these positive charges are going to flow up through R2 into the power rail and down the power rail through R1 and back to the negative side of the plates here. So it seems a little odd that the current's flowing up into the power rail, but that's what's happening because of the charge on the capacitor. And you know, according to Ohm's law, if you want current to go up, you know, this voltage is going to have to be higher than our power, right? Because that's what's going to make current flow in this direction. And so that's why you see that high spike. It's that high spike that allows the capacitor to discharge. And so by controlling or by you know, choosing these resistor values, we can actually control how that spike, how high that spike goes, because both of these voltages are going to suddenly jump to a kind of a steady state, one that you know, doesn't break Kirchhoff's current law or Ohm's law and allows the capacitor to discharge. And so I've done a bit of math here just to show how that works, and it's all just simple equations. So first is just V2 minus V1 equals the charge on the cap, which is VCC. And also, the current that comes down through R1 is going to equal the current that goes through R2, because that's Kirchhoff's current law. So I've written VCC minus V1 divided by R1 equals that current, and that also equals V2 minus VCC divided by R2. And after a little bit of math, we come to this equation, and this basically says how high that spike is going to be. V2 is our like spike voltage, and so that's going to equal VCC times 1 plus this term over here, R2 over R1 plus R2. So we see that it can never be lower than VCC. It's always going to be 1 plus something. And it has to be, because current is going to be going up there. But if we look at a few corner cases, the first will be, let me move this up a little bit. The first will be, if the two resistors are equal, well then this term becomes half. And so we'll get 1.5 our VCC. And that's kind of what we saw with the 10 kilo ohm resistors, right? It spiked up to 7.5 volts. Now, let's take the case where R1 is much smaller than R2. Well, in that case, this term is basically going to become 1. And so our current is going to spike up to 2 times VCC, or 10 volts in our case. And on the other side of that coin, if R1 is far greater than R2, then this term approaches 0. And if this approaches 0, well then our spike voltage is going to be like basically VCC plus like a tiny little bit. And that's just how we could eliminate that spike, by carefully choosing our resistor values. So if you guys stuck through the math part, I figure I should show a demonstration of that explanation on the scope. And So what I have here is I got basically have the same setup, and this time with two 10 kilo ohm resistors, and I have my probes on either side of our little capacitor here. And so basically this will be V1, and this probe here, the blue one's going to be V2. So let me energize this circuit. And so there we get our two spikes, and there's that top one that we want to get rid of. And if we zoom right in there, we see that that basically at V2, which is once we release the push button, it immediately jumps from 5 up to about 7.5, and then then the capacitor starts to discharge. And same with the V1, which is when we're holding it to ground, the push button. Once we release, it jumps right up to about 2.5, kind of halfway to 5 volts before it kind of, as it discharges, reaches the steady state at 5 volts. Now what we want is this cap, the R1, to be much bigger than this one. So right now they're equal at 10K, but if let me turn the power off. If I were to take this guy and replace him with a 1 kilo ohm, it would essentially be making the situation even worse, because now instead of being the same, it's going to be 10 times larger. And so I gotta put the power back on. And so if I hit the button, well, there you see, now it's just blasting right out of the screen. And I got to kind of put it to 2 volts per division just to see how high it gets. And if you could see the little number right there, it's about 9.5 volts, or 9.44 to be exact. At least the scope says that. And so it just makes the situation just way worse. So let's try the opposite side, where we have our R1 much bigger, and just to really show it, I'll put 1 kilo ohm here, and I'll put the big mega ohm resistor on this side. So we're gonna have like 1,001 difference, and this will really change things. And for this we could just go back to the normal time scale, because there should be no spike. And I put in the power, and let me put this back to 1 division. And so there you see it. We still have our negative spike going down, but there's just nothing there. There is no positive spike. And in fact, the charge of the cap is just it's all here, right? There's no jump. It just automatically starts the discharge. And another little thing you might notice is that for the yellow trace on this side with the 1 mega ohm resistor, he's no longer right at 5 volts like it was previously. And this is because of that big mega ohm resistor. Even though there's supposedly no current that's flowing, there's always some leakage current. And the leakage current is very small, but since our since our resistor is so large, you still get a bit of voltage that develops across it, and so that can be seen. And also there's some loading by our oscilloscope. Our oscilloscope is supposed to be 10 mega ohms, but since we're using 1 mega ohm, it's not like completely negligible. And that explains the slight difference, since around 4.5, 4.6 volts between the voltage. So if you made it this far in the video, thanks a lot for watching. Okay, see you guys later.